Okay. Okay, so back to the topic. The chained database is divided into two parts that changed some 3 years ago due to change in regulation on how to compute the energy performance of the building. So the two parts are called version 1.2 and version 2. We will focus on version 1.2, which is the data we worked on more. Version 1.2 contains each record of version 1.2, that is to say, each asset stored in the database is characterized by 35 features. So think about here we go. And so I was saying, think about the database is divided into two parts, version 1.2 and version 2, according to the different legislation on how to compute the energy performance of buildings. So we will focus on version 1.2. In version 1.2, there are around 1.5 million of data for each record, for each asset in the database. There are 45 different 45 different features, and we will have a look at some of them. So the first thing that you will face whenever you will want to work on data is the poor data quality that they have. This data, in particular, the data coming from energy performance certificate, are very, how can I say, dirty, because they are, there are many different persons assessing the energy performance of building with different background, with different experience, with different education, and so the data are very dirty, very contains many errors. So the first thing you have to do whenever you want to work on data is try to clean them. The most common error, the most common quality data quality issues you will find are missing values, inconsistent formatting of the data. So on a column, on a feature, you will have data formatted in different ways, duplicate records, outliers, and incorrect data type. Just to give you an example, in the chained database, the version 1.2 that we are working on, as I told you, there are 45 features, so 45 columns, and as you see, there are some columns, namely the one around 30, but even the one around 20, and one near, I think, is the 7th or the 8th, that contains a lot of missing data. So this picture just shows you how many missing data there are in a database. So this is why you need, first step of any data-driven work, to clean your data. To give you a picture of how the database is composed and on how we can work on it, I just focus on hospital buildings. In the database, there are 1,185 hospital buildings, and For each of them, you have 45 parameters to work on. I will focus my analysis here, and I will show you how we clean this data to have a reliable data set. And then in the second part of this bootcamp, Anya will show you how to code this data cleaning process. So let's focus on 8 parameters: the gross volume, the gross heated surface, the floor area, the surface over volume ratio, the walls, the roof and windows thermal transmittance, and the energy demand, the primary energy demand, which is called the APH. So I don't know how familiar you are with these characteristics, but if you think of each one and you take the average of each one, each number you have, it's a pretty fair number. So, for example, the average volume of 14,291 cubic meter is a fair average gross volume of an hospital building. So it seems to be correct. But and the same for the walls transmittance, for example, 0.96 kilowatt per square meter per Kelvin seems a reasonable number. And 44.6 kilowatt hour per square meter per year seems a good energy performance, energy demand for an hospital building. So just the average will not tell you how bad or how good they are, your data. If you look at the distribution in the picture on the right side of the slide, you will see that there are many outliers. The distribution is quite concentrated in one point, but there are some very high outliers. For example, look at the gross heated surface. Most of the buildings have a gross heated surface lower than 25,000 square meters, but there are buildings that has something like 150,000 square meters. So numbers very high. Or on the other side, if you look at the windows average thermal transmittance, there are windows here that has an average transmittance of close to 0, which is quite a round number for those of you who have some knowledge of thermal transmittance of windows. So what we have to do, and what we will do today, is to focus on these 8 parameters and try to find some the outliers or even errors in the database. This is a part of work that need a domain-specific knowledge. So in order to find the outliers, you have to define thresholds on the parameters, and these thresholds are can be defined by people who have a domain-specific knowledge. So in this case, who knows something about energy performance of buildings. So let's go and focus on the first parameter, the gross volume. The gross volume of the hospitals in the channel database span from 35 to 711 to more than 711,000 cubic meters. It seems very reasonable to think that it can be the interval can be shrunk down, deleting what it is too small to be an hospital, and what it is too big to be in hospital. In Italy, we have a law that states that the minimum height of an internal room should be 2.7 meters. So if we think about a minimum value for the gross volume of 27 cubic meter, it means that we are dealing with an hospital of 10 square meter. It's a very low value, but we keep it as a threshold. And the maximum threshold here is 25, we choose 25,000 cubic meter. More or less 75% of the data has a gross volume lower than 14,000 cubic meters. So that maximum threshold is it's still quite high. So it won't delay through hospital. It will only delay possible errors. We did the same with the gross heated surface. So the gross heated surface spans from 13 to 138,000 square meters. Again, a huge interval, and we shrink it down with a lower minimum on 10 square meter and a maximum of 10,000 square meter. Again, more than 75% of the data has a gross surface lower than 3,336 square meters. So our threshold will not delay through hospital, will only erase from the database possible errors. The minimum here is chosen 10 square meter because even if there is a law in Italy that state how much is the minimum surface of an hospital, the law, in the law, the definition of the minimum surface is given as a function of the number of patients in the hospital. So, and this data, the number of patients that can be ill, that can be treated in the hospital, is not given in the CENET database. So we cannot define a threshold according to the law. We compute the average age of the hospital, dividing the gross volume by the gross heated surface. And if you do that, you see that you obtain values from 1.4 meters to up to 50 meters. So you have hospitals where volume divided by surface, so the average height of each floor of the building is 1.4 meters, so for very short people, and some other where the average height of a floor is 50 meters, so very tall people. Again, these values seems to be incorrect or seem to contain some outliers that can be deleted. So what we did, we took the minimum the minimum value, 2.5 meters, even if most of the room of an hospital should be 2.7 meters high, as defined by the laws, but we want to be sure not to delay, not to accidentally delete hospitals where either the gross volume or the gross heated surface were recorded with a small error. And the highest value for the average height of a floor of the hospital is taken as 10 meters. Again, more than 75% of the data have an average age lower than 4 meters. So this maximum value, although not stated in the law, will not delay through hospital, will only delay fake data or incorrect data. The fourth parameter we look at is the envelope surface over volume ratio. So surface over volume is a very important parameter when computing the energy performance of a building, because it affects very much how the dispersion, the heat loss of the building. So we want to use this as an important parameter. If we look at the distribution of value inside our database, they span the value span from 0.08 to 2.41 1 divided meters. This is a very, again, huge interval. We shrink it down. Since we don't have any correct value or any value defined by the law as minimum or maximum, we took two thresholds, the minimum one, 0, and the maximum one, the mean plus 3 times the standard deviation of the data. Mean plus 3 times the standard deviation is a very common threshold when you deal with normal distribution, Gaussian distribution. So this is why we took this data. In this case, the threshold will delete only the highest value of the envelope surface over volume ratio. Fifth parameter, we start dealing with the thermal transmittance of the envelope. The database contains the average thermal transmittance of all the walls, opaque walls, all the windows, all the roofs, and all the basement. In the database, the average thermal transmittance of building walls span from 0 to 3.12 watt over square meters and Kelvin degrees. These are quite reasonable values, all of them. Anyway, we define two thresholds, the minimum 0 and the maximum 4. But think that nowadays the laws in Regione Lombardia state that the maximum value of the thermal transmission of wall, according to the thermal zone of the place, but it's something like 0.22 or 0.24 watt per square meter per Kelvin degree. So our threshold is really high, but we want to keep it because of very old hospitals, buildings where the walls were built 17 years ago, 80 years ago, and so this will account for, this maximum value will account for also for this older building. The average transmittance of the roof, again, we have a very huge span from 0.03 to 5.26 watt per square meter per Kelvin. And we use the same threshold as for the wall, so 0 and 4 watt divided by square meters and Kelvin degree. In this case, more than 75% of the data have a gross, have an average thermal transmitter lower than 1.48. So again, 4 is a very huge threshold, but in this case, some hospital roof, some data will be deleted because the maximum here is 5.26. Again, the laws in Region Lombardia now state that all the roofs of a building should have a thermal transmitter of 0.22 watt per square meter per Kelvin degree. Eventually, the last average thermal transmitter, the one of windows. Again, we have some windows with 0 as a thermal transmittance and some others with 6.42 watt per square meter per Kelvin degree. So again, a very huge interval, but we want to be on the safe part again. So we define a very large threshold from 0 to 10 watt per square meter per Kelvin, even though more than 75% of the data have an average thermal transmitter lower than 3.78 watt per square meter per Kelvin. And again, the law in Region Lombardia states that now the maximum thermal transmitter of a window have to be 1 watt per square meter per Kelvin. So our thresholds are very high. The last of the 8 parameters is the primary energy demand. In this case, we have hospital spanning from 0.32 to 698 kilowatt hours per square meter per year. 698, it's a huge number for those of you who are not aware on how much an hospital building can consume. Think that 75% of the data have an APH lower than 60, so this is close to 700, so it's sure is a wrong value. But again, we want to be on the safe side, and we use a very huge threshold in this case. So even the lower threshold is 0, and the higher threshold is 800. By the way, the law requires new building to be a nearly zero energy building. That is to say, an APH, a primary energy demand close to 0. And a Class G building, the worst building according to the Italian law, has an APH of around 160. So the 800 threshold is a very huge threshold. Even if we took very huge threshold, so threshold that are easily satisfied, we clean the data and in an iterative process, and we start with the 1,185 records, the whole hospital buildings in the database. We delete 154 records working on the gross volume, so around 13% of the database of the data were deleted. The second data cleaning was on the gross seated surface. In this case, we didn't delete any records because probably the ones who has some problems in the gross seated surface were already deleted because they had problem also in the gross seated volume. Then we delete records with the average A, so gross volume divided by gross surface, outside our threshold, so lower than 1.4 and higher than 10. And again, we delay, and in this case we delete we delete 8 records. Then we delete records with envelope surface divided by volume too high or too big, and in this case we deleted 12 records. The walls, the threshold on the walls average transmittance was not a problem for the remaining data, so the data that passed the previous check, so we didn't delete any. We delete one record when checking the roof average transmittance, 0 records deleted again when working on threshold with on the Windows average transmittance, and also 0 record deleted when working on the APH, on the energy demand. So of the 1,185 starting records, we ended with 1,010 records that we thought are a more clean, that are cleaner data, but they are still not clean enough, as you can see from this picture. This picture is a violin plot of the energy demand, the APH, so how much energy is needed to heat the hospital, divided according to the energy class of the building. So A plus, A, B, C, D, E, F, G. As you can see here, there is a high variability of the energy demand, and especially in class G, there are huge outliers. But this is not only a problem of outliers, so how much is the I of the violin plot. The problem is that somehow some violin plots overlaps on the y-axis. So, for example, if you look at the building in class D and the building in class A, what we know, what we think is that a class D building should perform better than an E class building, but as you see, the maximum of the violin plot of a class D building is higher than the maximum of the violin plot of E label building. So this overlapping is again a problem. So a further cleaning is needed. And the cleaning in this case was just deleting the outlier. So we delete the quantile, we delete the record below the 5% quantiles or above the 95% quantiles. And in this way, we deleted 106 records, so a lot of the records we had. But if again I look at the violin plot of the energy demand divided by class, as in picture, as here in picture on the right, you see that in this case the overlaps between the energy demand of different classes is no longer a problem, and that the violin plot, even of class G, which is still very high, is not as huge as it was before this last step. So this is more or less the process you will do in a few minutes with Anya. Let me just show you a brief recap of how problematic was our database. In this picture you see a lot of bars. Each bars correspond to a building, an intended use of the building. They are classified according to an Italian law. For example, A1, E.1 is are residential buildings, E.7 are school buildings, and so on. As you can see here you can see how many of for example, if you look at the A.1 bar, these are residential buildings for permanent use, and you see that we deleted in the whole process around 12% of the records. The bar is colored according to the error, so you can see that most of the error in residential building, the first bar on the left, are errors due to the energy performance, error number 9, the dark green. The second most common error is error 3, which was the one about the average age of the building, so the volume divided by the gross volume divided by the gross surface, and so on. Error 5 and error 4 are then also common error. If you change the destination and you go, for example, on E8 or E6, you see that error 6, which is the thermal transmittance of the walls, is a more common error than in other destination of the building. You can look at this data also flipped, so for each error from 1 to 9, how many residential, how many of each different use of the building are in each bar, that is to say in each error. In this case, there is a bias, let's say, because residential buildings are more or less around 45–50% of the whole database. So it's quite understandable that E1 is the most common error. And so you have to be astonished, for example, by how huge is how huge is the percentage of building of different the intended use in error 5 and error 6, which are the one related to the thermal transmittance, and where the error related to residential building are very few if compared to other destination. And here it ends my boring part, I think. I'm sorry to be boring, but if you want, now you can either use this QR or use the link that Anya is providing you in the chat, download the database you will work on in the next part of the bootcamp, where you will work on the data and start working with Anya. I just thank you very much for your attention, and if you have any questions, maybe we can answer them later after Anya's presentation. Anya, the stage is yours.
Thank you so much. So maybe, okay, perfect. So maybe in order to give a few minutes for everyone to download the file, if you have questions, you can either unmute yourself and ask or write in the chat. So we give like 4 or 5 minutes here till everybody downloads the file. So the first link I provided is the database that you're going to use. And the second one is the GitHub link to the full notebook. So you will see the notebooks of all these 3 sessions. The one that we're going to use today is the data cleaning one. So that's the one you can open up, and or not, you can just follow my instructions as I will share my screen and show everything. I think you have access. Is there a problem with the access to the Google Drive? Okay, I can share the file here directly for you to download. There is an issue with that. Can I share the file here?
What did you find?
Huh? So now the issue with the link is resolved. You can download it from the link. Yes, please try and tell us if it works. So in the meanwhile, I would like to thank Professor Cecconi for the very interesting and lucrative presentation. That is the result of couple years of research, I would say, in this field. And just a quick introduction about the bootcamp series that we're doing. So for those of you that attended our previous lecture series, we already explained it. For those that are new, so we won this research grant with CIB to do a couple of different introductory sessions or lectures or bootcamps on AI and machine learning application for building performance analysis, specifically energy analysis. And we had a very interesting summer school in collaboration with EC3 in Greece this year. We had this lecture series. We will have another one at the end of the month that I will share with you the information at the end of our session. And this bootcamp series we will have in 3 successive Wednesdays, and focuses on the practical part of how to use machine learning, how to code, to use the interesting data and interesting information already hidden in our databases that we have. So I guess most of you have already downloaded the file. Let me share my screen and start explaining on this. So, okay. Yeah, I cannot stress enough the fact that the precision and the performance of a good machine learning model is highly depending on the data that we're using, the data quality and quantity that we're using. So data cleaning probably is one of the most important steps of taking. That's why we delegated this entire session to that. So starting with any code, we need some packages. I'm not gonna go much into detail because I think most of you had at least an intermediate knowledge of Python, or machine learning. So I don't want to go so much into detail. You already have the file, but I will briefly just explain the different steps. So we are using the SciPy and Matplotlib mostly for this, which are some packages for graphical representation and also for different functions that we are using for the data cleaning. So we import all of these packages or specific, all of the libraries and specific packages that we need here as the first step. And we have to run this first line of the code to have all of them because we're gonna refer and use this. The second step is reading our database from the Excel file. So the file that you have downloaded, you have to upload it in the file section because we're going to use the local file here for the ease of references. So in the file section, here you can upload your file, and so I'm gonna go to my file. Okay, so now it's uploaded, and we can easily use this command of PD, which is from the Pandas, read underscore CSV and the path of our file. In this case, it is local, so we don't need to give a long path of the file, and we save it as a data frame that we're gonna use here. So I will run this code. And if you want to see how it looks in the Python environment, I can easily show this. Yeah, which gives us the same Excel file, but in a form of a data frame inside Python. That you see, we have all the different columns. We have 1,185 rows, which is the number of our projects that we have, and so many different columns, most of which we will not use. For instance, the place that it's located is not really useful for us at this moment. The third step is assessing the missing values in each column. So and we want to also plot it to graphically see which columns have the most missing values. So probably it's better to drop them, because if we have a lot of missing values in a column, if we have few of them, we can maybe replace it by some methods like putting the average one or etc. But when, for instance, 50% of the projects do not have that specific value, for instance, the location of it, it's better to not consider that column, because if you want to fill it, it will not be precise. So these are the main general configurations for our plots, like the resolution or the figure size. And we usually use the golden ratio for the figure for a nicer presentation. We're going to use a bar plot here. So PLT is our abbreviation for the Matplotlib that we're using. So plt.bar, and then it ranges from it ranges for the columns that we have, and in each column the number of missing values. So the comment dot is now shows the rows that have a missing value, and we sum it up to see how many we have. And we also define the labels as the database column for our X label and the Y label as the number of missing values. And then we show it. So if I run this code again, you see that for each of the 45 columns that we have, it shows that some of these columns have really high number of missing values. We have 1,185 projects, but some columns have almost the exact same number of the projects as missing values. So it means that the column is completely empty. So it's better to drop them. The fourth step is identifying errors in our database. In order to do that, the simplest way is to see if what is our mean value, what is our standard deviation, and what are the outliers that fall outside that -3 times and +3 times of standard deviation. That is a very common statistical method. So I will explain the first two, and then we'll run the code for the rest of them. So for the gross volume in the database that we have, we can use the NumPy.mean command to calculate the mean value of that specific column, which is called volume lordo in our database. So this is our database name dot the column name, and we calculate the mean of that. The same is for the standard deviation, that is np.std. I run this code, and it shows for this column what the mean value is and what the standard deviation is. The same for the grass-seated surface. We calculated the mean and the standard deviation. It's the same process for all the other 5 variables that we want to clean from the errors. These are the columns or the variables that we're going to use for our next analysis. That's why I'm not going to repeat the process again. The full code is here. And I will run it. You see, for the other ones, again, it gives us the mean and the standard deviation. Something really nice that we can do is using the describe command. So the name of our data frame .describe, which shows all the important statistical information, like the mean, standard deviation, the minimum value, maximum value, the 25th quartile, 50th quartile, and 75th quartile, which are important information for us. So if I run this code, it gives me that for all of the columns. But again, not all of these columns we're going to use. And now I'm going to plot the pre-cleaned data. So we have not removed any data yet, even though we have had missing values or errors in each of these rows. Just quickly going through the important information we have to include. Again, the figure size. Here we are gonna have 8 plots in 2 rows and 4 columns. So we're using the subplots command and defining the number of the rows and the number of the columns, the figure size that we're going to use, and then also the subtitle of each of them. So as you see, for instance, the first one is a histogram of our volume lordo, and we're going to do a histogram of the different volumes that we have. We want to see how frequent that is in our database. So again, we calculate the mean and the standard deviation. And we want to see how many of this data falls between that mean volume plus 3 times standard deviation and mean volume minus 3 times standard deviation. So in order to see our outliers. So we define these vertical lines that their X volume is on the minus plus 3 times standard deviation, and their Y volume is the maximum number of the records in there. And then here is the configuration and the style of the line that we want to have. For instance, we want to have a dashed line instead, and it's going to be orange. And we have an if comment saying that if the mean minus 3 times standard deviation is bigger than 0, then also do the same line for the other side. So we have one line for 0 for the mean plus 3 times standard deviation, which is a positive volume. So positive value. So we are going to definitely have that. But for the negative one, we have to make sure if it's not a negative value, because that doesn't make sense. And then also the title. For that, that we're gonna use. So if I plot this, it'll take a little bit while. Okay. So I do the same process for all of the 8 columns that we are analyzing. So you see, before cleaning our data, these are the number of records, and this is the gross hit volume, for instance. You see the majority of them are closer to 0, but we still have some outliers here that fall out of mean plus 3 times standard deviation limit, which is a very important limit to meet. The same has been done for the gross heated surface, gross volume divided by gross surface. In the gross envelope surface divided by gross volume surface, we have more outliers that is more evident here, and so on for all the 8 of them. So our purpose is to clean up these outliers because these outliers could be due to many things, like the errors of estimation, or I don't know, different measures of estimation, or some very unique buildings that we can easily drop from our database because we don't have enough samples like that to have a accurate prediction at the end. So moving forward to the cleaning data from errors and deleting outliers, at this point, we want to delete these outliers with the rules that we have. So the rules were completely introduced to you by Professor Cecconi. For instance, for the gross volume, we delete the ones that are less than 27 or higher than 25,000. So in order to meet that, first we start with the length of our data frame to see how many records in general we have. And then we say, okay, we start with 1,185 records here. This is our first number of records of the entire database. Then we want to drop it by .drop command. All those data in this volume order column that are less than 25, and when we put in place true, it means that replace the data frame with this new one. So technically, it's overwriting it. And so here we will see how many we started with the initial number of data, and then our new length of the data, our new data frame that has already deleted the data, the projects that have a volume order less than 27. And then we do the same process for the ones that are higher than 25,000. So again, we can do the same process here to say, okay, initially we deleted 0 too small records, so there were none that were less than 25. And then we end with 1,031 records because we deleted 154 records out of the 1,185, equals to 12% reduction, because those were the projects that had higher than 25,000 value for the gross volume. And then, yeah, we have the n value, which is our length of the new length of the data frame that we state here. And then this is like a very simple equation that we divide divide the n value, the n length of our data frame by the start length of it, and then do the percentage to see how much it has been reduced. We do the same for all the other, after this, we want to see, even if we deleted some outliers based on our rules, we still want to see that how many outliers we have that are falling outside the mean plus 3 times standard deviation and mean minus 3 times standard deviation limit. So in order to do that, we still calculate the mean value by NumPy.mean command of that specific column. The same for the standard deviation. And then we say, okay, this is the minimum value that we have, the maximum value. So these are all comments inside NumPy. And the limit is our mean value plus 3 times standard deviation. You see the number of upper limit is that. No, sorry. So this is the upper limit that we're calculating. And then we say, okay, number of upper outliers is the ones that if we locate them in our volume and order column, their value is higher than mean value plus 3 times standard deviation. And the lower outliers are the ones that have a less value. So by this command, by the length command, we calculate the number of these outliers. And if I run this code, you see that we have 12 outliers on the upper section and 0 outliers on the lower one. Now we want to plot the distribution of data with a focus on our error number 1. So again, I'm defining the resolution, figure size, and all the other configurations required for the plot. And here we say, okay, again, we are gonna show that limit lines by orange dashed line, as we did for initially in our steps of data cleaning. So we define the X value and Y value of this line, and then plot it with the X variables, Y variables, and the style of our line and the color of our line. And we say, if, again, the mean value minus 3 times standard deviation is not negative, also do it for the other side, for like, do the line, X variable of the line on the other side, and then plot it. So if I run this, you will see that as also calculated here, we have 12 outliers on the upper side of our limit that have a volume 3 times more, three times standard deviation more than the mean, but zero projects or entries that are on the lower side of the outlier. So we do the same process with the records with gross seated surface smaller than 10 square meters or bigger than 25,000. So it's exactly the very same process. So we initially define these rules here and delete the and replace actually the new database with the deleted data from it, and then compare how much data is deleted, how many data entries are deleted, and then we also calculate the upper outliers and lower outliers and plot it. So if I plot the second error or the second data column that we are focusing on, you will see that we started with 1031 records because already 100 and couple records were deleted from the first error. So we have less number of data here. We deleted 0 2 small records. So on the lower side, we didn't have any outliers, ending with 1031 records. So nothing deleted, but so it was 0% of deleting here. But we have the number of outliers on the higher than 95th quartile are 11. And as we plot it, we see it. But on the lower than 5% quartile, we don't have any. So we only have outliers here. Going through the same for error number 3, which is the average height lower than 2.5 or higher than 10 meters. You see, we started with 1031 records and 8 records were deleted in total. But we have, again, 12 outliers here on the upper side that should be deleted. The envelope surface divided by volume ratio. If it's like negative value or more than 3 times standard deviation plus mean. We started with 1011 records, reached to 1006 records, and we have only one outlier on the upper part here. Records with average wall transmittance below 0 or above 4. Again, the same process, but no data was deleted here. And again, we have only outliers on the upper parts, 7 of them. The 6th error is the record with average roof transmittance below 0 or above 4. So again, here we have only one data deleted regarding to the rule and one outlier on the upper part. We have the error number 7, records with average window transmittance below 0 or above 10. No data was deleted and there's no outliers here. So this means that data is either very accurately gathered or the projects with outlier have been already deleted on the previous phases. And finally, the record with primary energy demand or EPH below 0 or above 800. So again, no data is deleted, but we have 13 outliers at this part. So this is really good to understand what the status quo in our data is, even though we deleted the errors based on the rules that we had already, but still we have outliers. So another thing that we're gonna do in order to see how effective is data cleaning on our analysis and understanding our data is to do that volume plots. In order to do that, first we want to see how many unique energy labels we have in our data. So we describe a variable here called class energetic, which means energy classes, that equals to our data frame dot energy column of energy classes, which the name is this one, dot unique, to see how many unique values it includes. And then we sort these values alphabetically and show it here. So if you see, we have A plus till G energy labels. Now we want to see if we put it as a list here, we want to understand the EPH value for each of these records. So for each value that we have, what the energy, the EPH value is we have there, and add it to this list called EP underscore classy for the plotting in the next phase. So I'll do that. You see, like we have a long list of this. And then we want to do a histogram of each energy class to see, okay, for any energy class, how much this energy demand is distributed and what is the histogram of that to logically conclude that the worse our energy label is, the higher its energy consumption would be. We want to show that graphically. So again, I'm describing the configurations and the attributes of the figure here, and then do the histogram with the plt.hist command, where the energy demand of each value is as the x value, and then we do the coloring of that based on our different energy labels. And also we want to have the parameter of that as well in the histogram. So the label is the energy classes, and then in the type is histogram. We have also the legend here, which is this one. And then the X label and the Y label. So the X label is the EPH value and the Y label is the number of records. So if I run this code, you will see that, for instance, starting with the A energy label, mostly it's the histogram of the EPH value is concentrated more near 0, which means it is less energy consuming and more energy friendly. The A plus is performing even better. The further we go toward G, as you see, it's been distorted toward higher volumes. And in the energy label G, we have also so many scattered numbers, so many outliers, you'll say. So it's not as concentrated as other energy labels. So we can logically conclude that the buildings with energy label G might have even more outliers, or of course they're not do not have a proper EPH value and not energy friendly. So moving forward, we are going to do the violin plots of the EPH for each energy class. Again, these are the configurations of the plot. We start with the, okay. Yeah, so we want to, so the violin plot in general shows us the quartiles of our building. So we define the quartiles of 5 to 95%, which technically most of our data should be here. And the data that fall out of that are the outliers that we need to clean. So we say that for the data that is in our range of the energy classes, we will do the violin plot using this command in order to see which of them are in the 5th or 95th quartiles. And the rest is the titles. So if I run this code, you will see that for instance, energy label G, as we already knew, is very scattered, and there's not a very logical correlation. For instance, energy label F should perform worse than energy label E, but you see that there are many overlaps, and this is due to the outliers that we have here that need to be cleaned, that we already calculated in the previous section, that how many outliers we have for each of these, each of the columns. So if you move forward and delete them, so as you see, we calculate we create a new array of projects that for their EPH value that is inside our initial array. We only include the ones that are higher than np.quartile 5% and or lower than the quartile of 95%. So we only limit our data to the data that are between 5th and 95th percent quartiles, and do the plot again with the exact same comments. And as you see, it's been narrowed down to, and it's more concentrated, especially on the G-plot. And you can see the differences between all of these energy labels more evidently. It's not that there are so many overlaps. And finally, if we want to do the result analysis to see how many records were completely, like in general, deleted. So we describe this new variable called, like the new list called erased, and we range the length of this new the new array that we had, the EP underscore classy underscore RID, And we say like, okay, for the, we want to see the difference between the new one, the initial database that we had, the length of the initial data that we had with the new one. So it will give us the erased number. So if we sum it up, we'll find the complete numbers, the complete data that was erased, which is 107 records on this second round. And if we want to calculate do the histogram of erased records per energy class, again, we have these configurations of the bar plot, and we have the x as the the length of our erased numbers in each energy label, and then we have the energy labels on our x-axis, and on the y-axis is number of erased records. If I run this again, you will see the final records that we see that on the energy labels C and D and G, we have the most deleted records because there were more outliers here. And finally, we want to plot the clean data again. So you remember this plot here, show you the initial one. So the initial one was like this. We had so many outliers on some of these records. Now we want to see the difference after data cleaning. Okay, so as you see now, this data is more concentrated, and there are not many data scattered, especially on the x-axis. If you see, still, since we are plotting the 95th quartile, there are some records that fall out of that, but I mean, this is normal. And yeah, so comparing these two plots, you will see that data cleaning can increase the quality of our data and is a very important and necessary step in generating a model or doing further analysis. And all of these plots indicate that. So I will stop here, but I would like to see if you have any questions. You can either unmute yourself and ask or write in the chat section, so I can explain more on that if you have any specific questions.
This is only to confirm. The general approach is simply filtering out all data that it is out of the 3 standard deviations of the mean, correct?
So initially, we, as I told you, we did it in 2 phases. The first phase was to deleting the data that was not meeting some rules. For instance, if the height of a building, there was a record that its building floor height was less than 2.5 meters, this is a logical error. Even if that data falls inside the -3 times standard deviation, but logically it's a wrong record. It's not correct. So we initially deleted the data that was not meeting our rules and our standards. And this is coming from the background knowledge in the field. So this has nothing to do with the statistical side, but more on the rules and regulations that we have. And on the second phase, we deleted the data that was falling out of the 5th and 95th quartile, which is the mean plus and -3 times standard deviation.
Okay, thanks. Understood. And one more thing, this is not a question, it's more like a request. The file that I downloaded from GitHub, does it include the boxes with text that have
Yes.
a small? I mean, I can see them. I can see the code and the plots. Everything works fine, but the text is not included. I don't know if I have to try to download again to see if there was something wrong, but I don't know if someone else can confirm on this. But if it is the case that the text boxes are not included, could you share the version with those small clarifications?
Right. So the GitHub file, it should be more or less the same that I presented. I might add it like or divide it into more sections here for ease of explanation, but the codes are exactly the same. But I don't know, maybe we can share the Google Colab file or
Yes. I mean, just for example, that's those sections with computing the number of records, histogram of erased records per energy class. Those small explanations is that what is missing. But it's not great problem because at the end we have comments on the code, but
right.
I think they are useful.
So what we can do is that since we will share the recording of the session with you, we will also upload this updated file on GitHub and then share the new link with you through email. Because if
Sure.
you want to share the Google Colab, we should grant access to you, which is a slightly difficult process, but we can share the updated version on GitHub so that you can
Sure.
also read all the other comments and explanations in text.
Sure, that's perfect. Thanks.
You're welcome. So I'll stop sharing in order to see also the chat section. And in the meanwhile, that I wait for the questions, both on the chat or if you want to unmute yourself and ask, I just give you a quick preview of what we're going to do next week on next Wednesday. So the data that we have cleaned, we're going to use in order to cluster the buildings based on this data that we have, which is grouping them into groups with same characteristics and same attributes, which is an unsupervised learning type of problem based on the characteristics, which is this 8 columns that we have of each data. We're going to see how we can cluster our buildings based on energy related attributes that we have. So yeah, definitely don't miss that. It was going to be, we're going to little by little, step by step, show you how to develop and complete a machine learning based model that can cluster and analyze and predict energy related parameters. Okay, so if there are not other questions, okay, yeah, I see a raising hand.
Yeah, just a quick question. When doing clustering, are you going to use PCA? PCA, did you hear me? Yeah. Are we going to be
Yes,
using PCA? Okay.
So I thought you were
Principal.
asking. Yeah, I know what PCA is. We're gonna also use that, but I would want to double check with Professor Rucekodi. Because we have many different versions of the same problem. So we want to see which one we're going to present.
Okay.
Yes, so we are also going to use the PCA in the version that we're presenting next week.
Okay, yeah. Are we gonna discuss maybe a little bit on the theory, or are we gonna just jump to the code?
We can also include that in the theory. Yeah, if you're interested, we can definitely talk about it.
I am. That will be wonderful. Thank you.
You're welcome. Yeah, of course. So in the meanwhile, I want to share also something with you, a very interesting program that we have organized. And still, if you have questions, you can raise your hand or write in the chat, but let me share this before ending the session. So okay, so as I told you, and as some of you have already participated in our previous AI in construction lecture series, our October, so each month we are having one lecture series or one session. The previous one was more on the in synthetic data generation and generative models and this kind of topics that we had one industry professional, one leading researcher, and one PhD student following the same this session that we're going to have on October 30th that will be advertised to you, and you can register through this link. I will also share the registration link in the chat. Is more on computer vision and image processing. So, and we have wonderful keynote speakers. We have Luca Rampini from PwC Zurich, who is a senior associate in the business and data intelligence team, and who has also is a PhD alumni of Politecnico di Milano and has done wonderful research. Is going to presenting the topic on computer vision application for construction and facility management. We have Juan Diego Nunez Morales from University of Illinois at Urbana-Champaign, who is also a very leading researcher on the topics of AI-driven project controls in building construction, computer vision, production tracking, and AI-driven performance forecasting. And also we have Yu Wei Kao from Politecnico di Milano. She is a near graduation PhD candidate that her research is on deep learning-based label-efficient LOD tree building point cloud semantic segmentation, learning from weak supervision. So don't miss this session. You can both register by scanning this QR code, and I will also leave the registration link here, and I will share on my LinkedIn and through CIB channels and also Politecnico channels. So if you're interested, participate and let your friends that are working in computer vision or image processing or are interested to learn about these topics, let them know to participate. So I also maybe leave the registration link here so it's easier to access. Okay, so let's maybe wait for a couple more minutes to see if there's any questions coming up. If not, we will share with you the recording of the session with the updated GitHub file. And in the meanwhile, we would be happy to answer to your questions if later on you come up with any questions through email.
Thank you very much, Anya, Fulvio.
Of course, thanks for being here.
Could you tell us in advance which files will be used in the next session?
It's the clustering one. Yeah, it's a 309 clustering notebook. Oh, you mean like the database that we're going to use?
Yes, just it will. I guess we will have to use a different CSV, or do we have to extract it from the code that we use today?
No, we're going to use a different CSV, and we'll discuss to see if we share the file, the CSV file in advance or not, or during the session. So,
Okay.
Yeah, but you have the notebook anyways. But the file, I think we will share during the session, so that.
Okay, thanks.
Okay, thank you so much, everyone, for participating. We're so happy to have so many registrations and participants, and it was really nice to have you here and share our research and projects with you. Hope to see you all next week. And yeah, take care and see you next week. And thanks to Professor Recekoni as well for the interesting presentation again.
Thanks again.
Thanks. Bye.
Thank you. Thank you.
Thank
Have a
you,
good
guys.
one.